All right, in this video, we are going to talk about using NAND gates or NOR gates as universal gates to build any computer logic systems, right? NAND and NOR as universal gates. So the purpose is, if you think about the computer system, if you only have two types of gates in the computer logic, and you can just wire them up using some programmable hardware or software, so you can simplify the circuit a lot. Even though the trade-off is probably you have more gates, which are taking more space on the chip, but finally you simplify all the circuits into just two types of gates. And so today we're going to learn how we can convert complicated circuits into just NAND gates and NOR gates. Okay. And or not. So they are sufficient to implement any digital system. And if we can convert I just write it down, so in the future when you look at the notes, you know where this idea came from. Okay, if we can convert NAND or NOR to these three gates, then any circuits can be implemented by NAND or NOR gates. Okay, so let's start a new page to prove this statement here I just made. Okay, so first of all, let's look at NAND gate. NAND gate as the universal gate. So let's look at the logic expression first. So a NAND gate, which is actually A and B not equals to Y, right? If we want to make this one, for example, first of all, to a NOR gate, which is an inverter, what we can do is, Y equals to AB, that's a regular NAND gate. And if we short the two inputs, so it becomes A and A not. So A and A is A. So finally, it's going to be A not. To implement that into a real circuit, is actually you just need to short the two inputs, so they have the same input to the two inputs, and then the result will be A not. So that's an inverter using a NAND gate to make an inverter here in this type. Okay, that's a NOT gate first. So what about AND? So we know AND is A and B. And what we have for the NAND gate is A and B not. So the thing is, if we can have a NAND gate and then the inverter, you look at that. So AB here is AB not. Here will be AB not, which is AB. So the entire thing here right now is going to be an AND gate. So this is how you make it make an AND gate from there. Now let's look at OR gate. So we know that OR gate is A or B. Okay. If you want to make a NAND gate, you still remember the De Morgan's law? So what we did over there is actually this equals to you split the bar and change the sign, right? You split the bar, you change the sign. This is how this thing was described in the De Morgan's law. So we can use that for here. So for the OR gate, you have A or B. So it's going to equals to A or B, not. And then we can convert here, since we are changing the sign, so we get a chance to make an AND kind of AND logic from the OR. So since we are changing the sign, we convert it from the AND gate to OR gate to AND gate. So we get a chance here. So now let's move forward. We keep the bar on the top, and for this thing, we just make we split the bar and change the sign. Okay, so now it's actually already a OR gate. Oh, so it's already a NAND gate because you can see it's an AND and NOT. But we just need to invert them before we put them into this NAND gate. Okay, so now let's implement this in the real circuit. So we have A NOT, so AB here. So we'll need a NOT. Keep in mind, it's still NAND gate. We need a NAND gate here, right? NAND gate. So it's A NOT, B NOT. And then they are AND and NOT. So it's actually just NAND gate here. So this entire thing will be A NOT, B NOT, which is actually, because equals to, it's actually the same thing as the OR gate. But we are using a NAND gate to form an OR gate. So the entire thing here is equivalent to an OR gate. Okay. Try by yourself if you couldn't get it right now. Try to draw it by yourself. Okay. So we have NOT and OR, and now we need what about NOR gate? So use a NAND gate to make a NOR gate. How to do that? So we know a NOR gate. The logic for a NOR gate is A or B NOT. Okay, and there's no NOR or NAND or AND logic at all here. So we want to use De Morgan's law to change the sign. So the way to do that is without changing the thing here, is we have 2 bars on the top, so 3 bars in total, and we keep these 2 bars, and we change this one to A, B, like this. Okay. So we get a NAND gate here, and we have another inverter. So that's it. So we need an A, B, NAND gate. We need an inverter using the NAND gate, and then we NAND it together, and then we NOT it. Okay, so that's a NOR gate by using NAND gates. This entire thing here is, so this output here will be A or B NOT. Okay, so the entire thing here is equivalent to a NOR gate. The same stuff. Okay, then XOR. What about XOR? So we know the logic for XOR is this, okay? And what we are going to do is we are going to, since we know we can use NAND gates to make up OR gate here easily. So we don't care about the OR gate right now, but we are trying to convert these ones to something by using NAND gate. Okay, this is actually pretty straightforward. If you look at here, it's going to be A not B. You just put 2 bars on the top. Okay, then you get a NAND gate. Here, that's a NAND gate. Right, same thing to that one. Boom, boom. You got a NAND gate here. Okay, and then use the OR gate to put them together. Okay, now let's do it. So for example, we have A, B, and we have, here's A, here's A naught. Use a NAND gate to make an inverter. Here's B, here's B naught. Okay, so if you want to make this part, it's going to be A naught and B. So use A naught and B to as the 2 inputs for the NAND gate here. A naught and B, you want to NAND it together. Okay, that's this part. And you want to invert this part again, use the NAND gate. So you get this part. So that's A not B right now. You get this part on the left. And what about this part? Similarly, you can use A and B naught in the NAND gate. Here's A, here's B naught. Okay, in the NAND gate. And then invert it. Okay, so now you have this part and this part, which is A, B naught. And this, the logic for these 2 parts, the logic operation here is going to be an OR logic. So you can use this one, which is going to be, trying to just use this one as OR gate here. Invert, invert, and then NAND gate. Okay, so the final result here will be A XOR B. But if you look at the circuit here, you can actually simplify this circuit a little bit, because you can see it's inverted, inverted again, inverted, inverted again. So actually it's keeping the same value. So we can make it easier by redraw this circuit. Just redraw it. So it's going to be A, B, A naught, oh, B, B naught. Okay, and we need A naught and B to be NAND together, and we need A and B naught to be NAND together. And these 2 parts, you cancel these 2 things, and these 2 parts are being NAND further, so you get A XOR B. Okay, that's how to do it. What about XNOR? Use a NAND gate. So XNOR is A, B, A naught, B naught, and AB. Pretty similar concept, right? So you have A, B. So A naught, B naught is actually A naught, B naught, naught, naught. So that's how you can get a NAND gate here. It's the same thing. A, B is actually A, B naught, naught, and you get a NAND gate here. Okay. So now let's draw it. A, B, A naught, B, B naught. A, so here is A naught, B naught in the NAND gate. AB in the NAND gate. And then you need to invert it to make this term. You need to invert it to make this term. And then you OR them together. When you OR them together, same stuff, you need to reuse this circuit. The same thing, redundant. So just redraw it, then you can get something like this: A, B, A, B, A naught, B naught. So you have A naught, B naught to be NAND together, and AB to be NAND together. And then NAND. So that's actually A XNOR B. So that's how you make an XNOR gate use a NAND gate. All right, so what about NOR gate? So NOR gate can be used as a universal gate as well. So let's see. For NOT, first of all, for NOT, so NOT is, we know it's going to be A bar, and in the NOR gate, what we have is y equals to A or B naught, right? So if we make these two terms are the same, it's going to be A or A naught, so we can make an inverter. It's the same concept. If you have a NOR gate and you short the two inputs, then you are going to get A or A naught, which is actually A naught. So that's an inverter, right? Pretty simple. What about AND? So we know AND is this, and how can we convert the NOR logic to this? So actually we need a De Morgan's law, right? So A, here's a NOR gate, right? This is what is available in the circuit, and we want to use this one. So what we want to do is right? So De Morgan's law, so we can change the sign and split the bar. So now we are getting A naught or B naught. So now it's a NOR gate. The way to do that is you have A, B, you need to invert it. So here's A, you invert it by using a NOR gate. And here's B, you invert it by using a NOR gate. And finally, you NOR it together. So you can get y equals to A and B. Okay, keep going. So NOR gate, you can use NOR gate theoretically for any types of logic gates. We'll see. So what about OR? So we know OR, the logic for OR is A or B, right? But you have NOR right now. So it's actually super simple. You have a NOR gate, AB. Here will be y equals to A Yeah, so the only thing you need to do is get an inverter here using a NOR gate. So you can get A equals to A or B, Y equals to A or B. That's the only thing you need to do for the OR gate. Okay. Now the next should be NAND gate. How can I convert that into a NAND gate? So we know the NAND gate is like this, right? So the way to use the only gate available in the circuit, which is a NOR gate, to form a NAND gate, which is you can add 2 bars on the top, and now you can split the bar and change the sign. So you're getting 2 bars and A not or B not. So this little thing here is a NOR gate, right? So now we can do it. You have A, B, you need to invert it first. So use a NOR gate to invert it. So you have these 2 terms right now. And then NAND gate, NAND them together. NOR gate, NOR them together, and then invert. Okay, so that's A, Y equals to A, B. That's a NAND gate by using NOR gate. So next, we need a XOR. A bit tough. So XOR is A not B or A B not. And we need a NOR gate for that, right? So since we know how to make an OR gate here, so we just ignore this one right now. So we just trying to make up these 2 terms using a NOR gate. So let's see, A not B. How can I make a NOR gate out of it? So apparently, De Morgan's law as well, 2 bars on the top. So you are going to get A bar bar or B bar bar, which is A. So you get NOR gate. That's a NOR gate, right? Similarly, you can do it for this guy, A B bar bar bar, and A bar B bar bar bar, which will be A bar B bar. So we are using De Morgan's law a lot here. So make sure you go back to the equations and remember how that works. Okay, it's actually not that difficult here so far. So now we have all these things already. Now let's draw the circuit on the next page. So that's a NOR gate. So we have A, B, that's A, that's B, that's A naught, that's B naught. So A and B naught for the 2 inputs for the NOR gate, A, B naught, that's the first term. And the second term, A naught and B. And finally, these 2 terms should be ORed together. So we have an OR gate using a NOR gate. So we just directly use it here. You need this first, and then you need an inverter. Right. So that is A XOR B using the NOR gate. Okay. Now the last one, XNOR. How do you make XNOR gate by using a NOR gate? So XNOR, the logic expression for XNOR is this, right? Same strategy here. So we just do them separately. A naught, B naught, you need a NOT, B NOT, bar on top, 2 bars, okay, not this one, sorry for that. 2 bars, and then you keep the top one, and then make this part to be a NOR gate, so which will be you split the bar, split this bar, and change the sign, right? So finally it's going to be A or B. That's a perfect NOR gate. So what about this one? So same concept, boom, boom. And you want to split this bar and change the sign, which is, and that's it. That's a NOR gate. So the way to do that is A, you have B, and get inverted. So it's an AB NOR gate. So AB NOR gate, A NOT B NOT NOR gate, A NOT B NOT NOR gate. And finally, these 2 parts to be ORed together. That's an OR gate. This part is OR gate. So you need a NOR first, and then inverter. So this part will be A XNOR B, right? Okay, so that's it. That's everything you need to know for using NOR gate or NAND gate to form any other types of gate in the circuit. So that's how we can use these 2 gates as universal gates for digital logic design. Okay, thanks for watching, and we'll see you in the next video.